All right, so this is part 2 to section 1.4, and I'll be going through some examples in this section, or in this part of the section. I would probably make a part 3, going over different type of examples. So this first thing I'm going to talk about, that's actually in the textbook, and it's in the very beginning of the section where they go through some example, and it's example 1 on page 75 is what I'm about to go over right now. So it says, discuss the continuity of each function. So part A is f of x equals 1 over x. Part B is g of x equal to x squared minus 1 over x minus 1. And then part C is h of x equal to x plus 1 if x is less than or equal to 0, and then x squared plus 1 if x is greater than 0. So I'll make a note that this function for part C is called a piecewise function. It's defined into two separate pieces, or two pieces, x plus 1 and then x squared plus 1 are your two pieces. And it's defined for certain conditions. So it's the top piece if x is less than or equal to 0. It's the bottom piece if x is greater than 0. All right, so what I did was I went ahead and worked these out, and the solutions are in green, and then made some comments. So f of x equals 1 over x. Its graph, you'll see, is in the bottom, so this is its graph, so it's in blue. And there's a vertical asymptote, that's the y-axis. That's what x equals 0 is, that's the y-axis. So the graph itself is never going to cross the y-axis. And the vertical asymptote means that you can't have the function itself be defined at 0. So that's why its domain is all real numbers x, where x is not equal to 0, because you can't divide by 0. If you had to plug in 0, you would have 1 over 0, which is not defined. So the function's domain, the inputs, what can be input, go inside of the function. So the inputs, it can be any number x, but it just can't be 0. And that's due to the vertical asymptote that's at 0. Another way of writing the domain in interval notation is negative infinity to 0, and then union 0 to positive infinity. And so that U symbol, that means union. All right, I'm conjoining the two intervals, negative infinity to 0, conjoined with the interval 0 to positive infinity. Once I take that combination of those two, then that means I have the entire domain. In the last video, we talked about continuity and discontinuity. The vertical asymptote is a discontinuity, and it's non-removable. So there's a non-removable discontinuity at x equals 0. And then, but for all x in the domain, the function is continuous. There's no holes or gaps or anywhere in the graph itself that's in blue for its domain, since the domain does not consist of 0. All right, and that's how I would discuss the continuity of that function. Part B is g of x equal to x squared minus 1 over x minus 1. And I wrote it like a comment. If you were to factor the numerator of g of x, that turns into x minus 1 times x plus 1, which means you can divide out the x minus 1s from top and bottom, which leaves you with x plus 1. Now what this does is it rewrites g of x into an equivalent function, where the equivalent function is x plus 1 after you cancel out the common factors. Now, whenever you cancel out common factors like this with x minus 1, it's going to indicate that there's going to be a hole in the graph. So when you cancel common factors, there's going to be a hole. All right, after the dividing out of common factors, you end up with this x plus 1. So the g of x function is equivalent to x plus 1, which is a line with a slope of 1, y-intercept of 1. So it's going to be equivalent to that with the caveat that it has a hole in the graph at 1. And so here's its graph. So like I said, it's going to be this, it's going to be a line. So we have this line, y-intercept is 1, and it has a slope of 1. Now we have the hole in the graph is 1, 2 is the coordinates. So because of this hole that occurs at 1, we would say the domain is all real numbers where x does not equal 1. So x can be any value but 1. As an interval, that's negative infinity to 1 union 1 to positive infinity. And so I discussed there's a hole in the graph at 1, 2, which means this is a removable discontinuity because I can redefine the function so that it can be connected by enclosing the hole. So this is a removable discontinuity where in part A, this was a non-removable. There's no way I can redefine the function to make it connected since we have a vertical asymptote. And one side goes up to positive infinity, the other side goes down to negative infinity. There's no way I can connect that. Now for this one, for the removable discontinuity, there's a way to redefine it. Just enclosing the hole makes the graph connected without having to shift anything else or any part of the graph. So removable discontinuity at x equals 1, because the domain is all x values but 1, the graph is this line, and since the line's continuous everywhere, so it's going to be continuous for every x in its domain. Again, we're not including the hole as part of the domain. All right, so that is the details for that one. And the thing is, if you factor the function and you can divide out common factors from numerator and denominator, that factor that cancels out gives you the value for where the hole is going to be in the graph. And if it's x minus 1 is its factor, to get the hole itself, you just, whatever the factor is that cancels out, you set it equal to 0. So I set x minus 1 equal to 0. That's going to be x equals 1. You isolate x by itself. That particular value is going to tell you the x value where the hole occurs. So this is the x value for the hole. And because it was a hole, it was a removable discontinuity. Now part C was the piecewise function, and I wrote it in 2 different colors for each piece. I used blue for the top piece and yellow for the bottom piece. And so for the blue piece, just focusing on that, x plus 1, that is a line, slope of 1, y-intercept of 1, but that's specifically defined for x is less than or equal to 0. So I'm starting at 0 for x, and then I'm going down to negative infinity for the rest of the portion of that blue line. So that's just for the blue line. And then for the other piece, the gold or yellow piece, it's x squared plus 1. And we know for x squared, that means it's a quadratic function. A quadratic function has a parabola type of shape. And that's where I start out around 0. So since I have less than or equal to 0, I still have a closed dot at 0. But for the gold piece, it's technically would be a hole for the gold piece, but still enclosed if for the entirety of the function, since the blue piece has the point included. And so it's this parabola type of shape for the second piece of the function. And so considering the two pieces together, it makes the whole graph connected. Since the whole graph's connected, that means there's no holes or breaks in the graph, which means there's no discontinuities, which means the function's continuous everywhere. And it's continuous everywhere, meaning it's negative infinity to positive infinity, every x value, which is what the domain is. If I make a comment that if, let's just say, so this will be an aside. If I had h of x, instead of being x plus, x less than or equal to 0, if it said x less than 0, and then we still have the same thing, x squared plus 1 if x is greater than 0. So now the inequality does not include either one of them, includes the equal to sign. So neither inequality includes the equal to portion of the inequality. And what this means is you're not including 0 in the domain. So not including 0 in the domain. So that means so we would say the domain's like negative infinity to 0 union 0 to positive infinity, any x value but x being 0. And its graph would look just like the one we had before. It's just at 0, there's going to be an actual hole in the graph. So its graph will look just like how we had it. Except there's going to be a hole right here. So it's going to have that line portion and then this parabola portion. The only difference is now I have a hole. And that's 0, 1 is the hole. Which, since I have that hole, in this case, that would be a removable discontinuity. All right, so that's just an aside. That's just a subtle difference. If the inequality signs, if neither one of them has the equal to portion. And for this one, the original problem, it had less than or equal to 0. So it had that equal to portion, which mean I had the enclosed dot at 0, specifically 0, 1, right? Because the y-intercept is 1. All right, so those are those examples. That gives you a rough idea of determining continuity and categorizing any discontinuities as a removable or non-removable. So for this part C, there was no discontinuities. Part B had a hole, and that hole is a removable discontinuity. Part A had a vertical asymptote, and that vertical asymptote means it's a non-removable discontinuity. Now, I was able to determine without graphing it yet, there was a hole when you canceled out the common factors. So there's sort of techniques that you can apply algebraically. Of course, I would recommend sketching the graph to get a better picture, a better feel of what's going on. But here's a strategy. We're finding domain holes, vertical asymptotes, specifically for rational functions. So functions that consist of a polynomial in the numerator and a polynomial in the denominator. And this could be without having to graph yet. So you can make these conclusions without graphing. So if we're finding the domain, you're going to find any x values at first in which make the denominator equal to 0, since you can't divide by 0. All right, then you're going to exclude such values. All right, that's how I would do the domain. For the holes in vertical asymptote, you're going to factor the numerator and denominator. Now, if any common factors divide out, this will give a hole. All right, so if any common factors divide out, this will give a hole. Then after you cancel out the common factors, if there are any, so there might not be any common factors, but let's say after you factored and you were or were not to cancel out common factors, you would find the vertical asymptote by setting the new denominator equal to 0. All right, so this is a strategy for finding holes, domain, vertical asymptote. And the holes generally give you a removable discontinuity unless the graph is broken up into two pieces. The vertical asymptote gives you a non-removable discontinuity. All right, I'm going to apply this to the following problems. So for the following, find any x values for which f of x is not continuous, categorized as removable or non-removable. And part A, f of x equals 4 over x minus 6. Or sorry, not part A, number 40. All right, so number 40, 41, 45, 47, these are regular rational functions. I'll talk about 49 and 51 in a bit. Those are going to be, I'll handle those a little bit differently because number 49, you have this absolute value sign, and number 51 is a piecewise function. So for number 40, there's no, I mean, if I were to determine the removable or non-removable discontinuities, I basically need to determine, are there any holes? Vertical asymptotes. There's no factoring can be done. It's already reduced. So this is already reduced. So I can go ahead and just set the denominator equal to 0 to find the vertical asymptote. All right, so that's x equals 6. That's a vertical asymptote. Since it's a vertical asymptote, that means it's a non-removable discontinuity. All right, so that's the answer for that one. There's no holes because there's no factoring I can do to cancel out common factors. It's just a horizontal, or sorry, vertical asymptote at 6. And vertical asymptote is always a non-removable discontinuity. Now 41. That is f of x equal to 1 over 4 minus x squared. Now, if you tried factoring this is a difference of squares, and so this would factor to the following: 1 over 2 minus x, 2 plus x. Now, there's no common factors I can cancel out from top and bottom, so that means there's going to be no holes to the graph. So I can go ahead and set the denominator equal to 0. So this is already reduced. So I set denominator equal to 0, and that will give me the vertical asymptotes. So they'll have two options. There's 2 minus x equal to 0. Then there's 2 plus x equal to 0. If I solve for x, so this one you subtract 2 from both sides, you get negative x equal to negative 2. Then you divide by negative 1. So that's going to give me 2. And this one you subtract 2 from both sides, that's going to give me x is negative 2. So these two are your vertical asymptotes. So since they're vertical asymptotes, that means there's two non-removable discontinuities. And it's negative 2 and 2. All right, and they're non-removable because they're vertical asymptotes, and they're vertical asymptotes because there's no cancellation of factors from top and bottom, which would have given me a hole. Now for number, let's see, the next one's number 45. And it's x over x squared minus x. So I'm going to try to factor. So up top, there's no factoring. I just keep it as x. On the bottom, x squared minus x can be factored. They share x in common, so I can factor out x. And that's going to leave me with x times x minus 1. Now here's an example where I can divide out common factors. So I can divide out x. So this means there's going to be a hole. Dividing out common factors. That means there's a hole. And the hole occurs. And you set the factor equal to 0. It's just simply x equals 0 since the factor is just x. So you set, and the factor is just x, so that's why we have x equals 0. That's a hole in the graph. Which generally the hole means, unless it's a piecewise function, it means there's going to be removable discontinuity since it's a hole. All right, so just from that little bit, I can determine removable discontinuity at x equals 0 because there's a hole due to the cancellation of common factors from numerator and denominator. Now, after I've canceled out the common factors, that leaves me with 1 over x minus 1. From here, I can determine there's a vertical asymptote because I can't divide by 0. So by the vertical asymptote, you set x minus 1 equal to 0. You get x equals 1 is the vertical asymptote. Since it's a vertical asymptote, that means it's a non-removable discontinuity. All right, so in conclusion, there's a hole at 0, that's removable discontinuity. There's a vertical asymptote at 1, that's a non-removable discontinuity. And this follows from my strategy. So for finding holes in vertical asymptote, you factor numerator and denominator. Any common factors that divide out, this gives you a hole. After you cancel out the common factors, you find the vertical asymptote by setting this new denominator equal to 0. So after I canceled out the common factors, the new denominator was x minus 1. Setting that equal to 0 gives me x equals 1. So that's going to be the vertical asymptote. All right, so that's number 45. The next one's number 47. All right, so like before, I'm going to try to do some factoring. Top part, you just leave as is. There's no factoring for the numerator. The bottom part, this can be factored. All right, because of the x squared, so I'm going to have two factors where I have x and x. Because of the x squared, then I look at what two numbers give me negative 10 that add up together to give me negative 3. And it's going to be 2 and negative 5. And you can FOIL this and you'll get x squared minus 3x minus 10. So here I have common factors of x plus 2. All right, so since I'm canceling out common factors, that means there's going to be a hole. So there's going to be a hole, and that you set the common factor, which you're canceling out, equal to 0. So I set x plus 2 equal to 0, and you'll get negative 2. So there's a hole at x equals negative 2, which, since it's a hole, that means it's going to be a removable discontinuity. All right, so that's part of the answer, is I have a removable discontinuity that x equals negative 2 because it's a hole. Now, what I'm left over after the canceling out common factors, you get 1 over x minus 5. So I set the x minus 5 equal to 0. That gives me a vertical asymptote. All right, so 5, x equals 5 is a vertical asymptote. And since it's a vertical asymptote, that means it's a non-removable discontinuity. All right, and that's how I would handle those these examples so far. Now these last two, 49 and 51, are a little bit different than the previous ones, because 49 has an absolute value and then 51 is a piecewise function. So I'm going to discuss these two more in depth. So 49 is the absolute value of x plus 7 over x plus 7. All right, so you have to recall the definition of absolute value. So if I have the absolute value of x, that's a piecewise function. It's equal to x itself if x is greater than or equal to 0, or it's negative x if x is less than 0. So there's two conditions. Now, if I just talk about just f of x equal absolute value of x over x, depending on which case I'm going to be in. So if x is greater than or equal to 0, then this will equal x over x, which will give me 1. Now, if I had x less than 0, by our definition, that's going to be negative x over x, which gives me negative 1. And if you were to graph this, all right, so let's say 1 is right here, negative 1. Now for the portion in which x is greater than or equal to 0, I get it to be equal to 1, and that's for all x. So starting at 0, it's 1, and then everything to the right of 0, it's also going to be 1. So it's going to look like this for that portion. So this is the f of x equals absolute value of x over x, which eventually just equals 1 if x is greater than or equal to 0. I'll use a different color for the other portion. The other portion is negative 1, but since it's less than 0, I put a hole here. I don't include that. And then everything to the left of 0, it's negative 1. So that portion, it's f of x equals absolute value of x over x, which we said comes out to be negative 1 if x is less than 0. And since it has a less than sign, that's why there's a hole. All right, and since there's a break in the graph, there's no way I would can connect the graph because I would have to shift one of the portions up or down. So since there's a break in the graph and that occurs at 0, and further we have this hole down here at 0, then because of the break, I can't necessarily just enclose this. If I enclose that hole, then that doesn't do anything different because I still have this break in the graph. It's still discontinuous at 0. And that's going to make this non-removable discontinuity. Because I'd have to physically shift the function or the graph of the function for one of the pieces up or shift one of the pieces down. So this is non-removable discontinuity. All right, I just figured I'll talk about just this first before I do 49, but it's going to be very, very similar to this. And I'm going to be using the definition of absolute value. So now I'll go on to 49. So the definition of absolute value was absolute value of x is equal to x if x is greater than or equal to 0. So consider the x plus 7 as our x in this case. So I would say the absolute value of x plus 7, it's broken up into two pieces. In this case, instead of just x, it'll be equal to x plus 7. If, and again, instead of using x greater than or equal to 0, it'll be x plus 7 greater than or equal to 0. And then the other portion is going to be, instead of negative x, it'd be negative, and I'm applying the negative to the entire quantity x plus 7, so negative parentheses x plus 7. And that's if this x plus 7 is less than 0. And you could write this further by isolating x by itself for these inequalities. Let's see, so if x plus 7 is greater than or equal to 0, then that means x is greater than or equal to negative 7. And then for this one, that means x is less than negative 7. Okay, so maybe I'll write it like this. So I have two cases, right, because it's a piecewise function, so I'd handle each case separately. So the first case is if x is greater than or equal to negative 7. Then the function f of x, which equals x absolute value of x plus 7 over x plus 7. That's going to be equal to, so I'm focusing on the first case, that's equal to x plus 7 over x plus 7, so that divides out to give me 1. So when x is greater than or equal to negative 7, the graph eventually equals 1, or will simplify to be just 1, which is like how I handled this, where it equaled 1 and it was this horizontal line at 1. So this is going to be the same thing. We're going to have a horizontal line. Y equals 1 when the x values are greater than or equal to negative 7. Now the second case, let's say I do a different color for that. I'll do yellow. In the second case, that's for when x is less than negative 7. So based on our definition, this will be equal to negative parentheses x plus 7 over x plus 7. And I can divide out the x plus 7s and be left with, because of the negative, we'd be left with negative 1. So just like how I did this easier example, simplified example of this, where I got negative 1, and that gave me this other horizontal line. So this is going to be a horizontal line, y equals negative 1, when x is less than negative 7. All right, so now for the graph itself. All right, let's say -7's right there, and I know, so there's 1, -1. I know at -7, and then everything to the right of -7, I have a horizontal line where it's y equals 1. So that'll be like that. So that's my top part. So that's f of x equal absolute value of x plus 7 over x plus 7, which eventually gave me 1 when x is greater than or equal to -7. Now the other piece is just another horizontal line, but going in the opposite direction and at -1. And this other piece, it's going to be a hole because I have a less than sign. So I'm not including -7 when I have just the less than sign. That's why I have this hole, and then everything to the left of -7, all right, it goes forever to the left. So let's imagine that's a horizontal line at -1. Okay, so that's f of x, absolute value of x plus 7 over x plus 7, which is -1 for x is less than -7. And you'll notice, just like how I had in this simplified version, I still have a gap or a break in the graph, just like I have this break in the graph for this one. So that break in the graph, that occurs at -7 when x is -7. And since I can technically, if I were to try to redefine the function and enclose the hole down here, that doesn't make the graph connected because I still have this break in the graph. So since I'm going to still have that break in the graph, no matter if I redefine the function at that hole, this is going to be a non-removable discontinuity. So non-removable discontinuity at x equals -7. All right, so that's the answer for that one. Now the last one deals with this other piecewise function. And what I would do for this one is try to see what its graph looks like and see if the two pieces connect. If they don't connect, like in the case with 49, then it's going to be non-removable discontinuity wherever the break is in the graph. All right, so I wrote the function down, f of x equals, and it's piecewise broken up in these two pieces, 1/2 x plus 1, that's if x is less than or equal to 2, and then 3 minus x if x is greater than 2. Now, like with the absolute value function, like for this, there was a break in the graph, and that occurred at -7. Now, the question is there a break in the graph for this one? And there'll be a break in the graph. So I'm saying, question, is there a break in the graph at 2 in this case? Because that's where we're specifying for the different x values for the different cases. Is there a break in the graph at 2? And you can determine this if the two pieces do not connect. So to determine this, see if the both pieces equivalent to one another when x is 2. All right, so for the first piece, so 1/2 x plus 1, if I plug in 2, that's 1/2 times 2 plus 1. So 1/2 times 2 is 1, so 1 plus 1, that gives me 2. That's for the first piece. The second piece, I know it says greater than 2, but we're going to cheat a little bit just to hypothetically see if it were to connect. We know there's going to be an actual hole at 2, but if they were to connect, then even if there were a hole, there's a hole for the bottom piece, because the top piece has an equal to sign for its inequality, it'll end up being an enclosed hole. Or sorry, just not a hole, be a dot. So for the 3 minus x, plug in 2 to see what it becomes. So that's 3 minus 2 is 1. Now notice they're not equal to each other. So that means it's both of them, they're not going to connect. The graphs for the two pieces won't connect, which means there's a break in the graph. So the graphs for the two pieces won't connect. That means there's a break in the graph or a jump. And that break, that's going to be occurring at 2. Since it's a break in the graph, I can't redefine the function because they're both different values. I'd have to shift one piece up or shift one piece down. So that means it's a non-removable discontinuity. All right, and really that does answer the question. Now, if I wanted to actually graph the two, so really I'm done right here because it's just determining is it removable or non-removable. So that is the answer. But let's say I wanted to graph this. So I'll handle each piece separately. So the first piece is 1/2 x plus 1. And that's when x is less than or equal to 2. So what I would do is plug in some values for x. We already plugged in 2, so when you plugged in 2, that came out to be 2. Now an easy one's plugging in 0, because that'll give me the y-intercept is 1, right? So plugging in 0, 1/2 times 0 is 0, plus 1 is 1. And really that's all I need, right? Because this is a line. So all I need are 2 points. 0, 1, and 2, comma 2. I can graph that. Zero, 1. Yeah, and then 2, comma 2. And I'm only focusing when x is less than or equal to 2. If you wanted to basically, I just need these 2 points. So the only direction I'm going to be going is to the left. Are we going to the left of that forever because I'm dealing with less than or equal to 2. All right, so that's for that piece. The other piece, I'll do yellow. And the other piece was 3 minus x, if x is greater than 2. Well, we already know, kind of cheated a bit, but if x were to be 2, we know that that came out to be 1. So there's going to be a hole at 1, 2. Let's see. So yeah, because there's going to be at a hole at 2, 1. Sorry, I had it backwards. So when we tried to see if the two pieces connected, we plugged in 2, even though the bottom piece was technically defined for x greater than 2. So because it's a greater than, that means there's going to be a hole at 2. And the y coordinate of that hole is going to be 1. So 2, 1, there's a hole. All right, so there's a hole right there. Now I want to pick some values that are to the right of 2. So let's say I picked 3. That's an x value to the right of 2. So plugging 3 in for x, that makes 3 minus 3, which is 0. So that means I have 3, 0. So I have that point. And we know this is a line, and it's got a -1 slope. And if I wanted to just do one more, let's say I've plugged in 4, since that's to the right of 2. 3 minus 4, that's going to give me -1. So you could do that one. That's 4, -1. This is 3, 0. And I just connect it. And I have that hole. And then it keeps going down like that. So those are my two pieces. All right, the yellow piece is 3 minus x when x is greater than 2. And then I have the other line, the blue piece. One half x plus 1 when x is less than or equal to 2. And because these two pieces don't connect, there's that gap or break in the graph. It's a small little break. That means it's non-removable discontinuity. And that occurs at x equals 2. So you could graph it and get to that same answer, which is more obvious. But I went ahead and just determined, is there a break in the graph? Because I know it's going to be two pieces. It's a matter of, do the two pieces connect? And to see that, you just plug in the x value for which the conditions are applying to. So in this case, the conditions are applying to the x value 2. And I plugged 2 into the top piece and got 2 as its y coordinate. Plugged 2 into the bottom piece and you get 1. Since it's 2 and 1, they're not equal. So that means the graphs are not connected. And I would have to physically move one of the lines to make it connect to the other one. I can't make it can't just enclose the hole and it be connected. So that's a break in the graph. And since it's a break in the graph, that's non-removable discontinuity. All right, that's the quick way to do it. not having to graph it. This is a long way to do it, actually graphing it and handling each piece. All right, so I'm going to make a part 3, and part 3 shouldn't be as long as this part, but part 3 will cover examples of one-sided limits.